In this first section of 8.3, we're going to talk about a new distribution. We're not going to be always able to use the normal curve. So we need to use a t-distribution when we don't know the population standard deviation, which I hope you can realize that it's not very common that we would know the population standard deviation. So when the sampling distribution of x bar is close to normal, we can find probabilities involving x bar by standardizing and finding x bar minus the mean divided by the standard deviation. But if we don't know standard deviation, we can estimate it by using the sample standard deviation and what happens when we standardize. When we standardize based on the sample standard deviation, our statistic has a new distribution called the t-distribution. It has a different shape than the standard normal curve. It's symmetric with a single peak at 0. However, it has much more area in the tails, as you can see in these diagrams. The top graph is a t-distribution graph. The bottom graph is a normal distribution graph using a population standard deviation. Like any standardized statistic, t tells us how far x bar is from the mean mu in standard deviation units. There's a different t distribution for each sample size, specified by its degrees of freedom. So the one thing we have to do with a t-distribution, this is also in the back of the book, I believe it's table B, we have to find the degrees of freedom. And basically the degrees of freedom is just 1 minus the total sample size. So when we perform inference about a population mean, mu, using a t-distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size n, making the degrees of freedom n minus 1. So we will write the t-distribution with n minus 1 degrees of freedom as t to the n minus 1. So the conditions for constructing a confidence interval about a proportion. We draw a simple random sample of size n from a large population that has a normal distribution with a mean of mu and a standard deviation of sigma. The statistic t has the t-distribution with degrees of freedom of n minus 1. When the population distribution isn't normal, this statistic will have approximately a t to the n minus 1 distribution if the sample size is large enough. So we'll talk more about the conditions here soon. When comparing the density curves of the standard normal distribution and t-distribution, several facts are apparent. So we have a couple of things going on here. We have the purple curve, which is standard normal curve. We have the teal curve, which is t with 9 degrees of freedom, and the dotted red line, which is t with 2 degrees of freedom. T-distributions have more areas in the tails than the standard normal distribution. They're similar in shape to the normal curve. The spread of the t-distribution is a bit greater than it is for the standard normal distribution, and they have more probability in the tails and less in the center than the standard normal curve. But you can tell they're very similar. As the degrees of freedom increase, the t-density curve approaches the standard normal curve ever more closely. So here we go. What's the critical value t star from table B should be used in constructing a confidence interval for the population mean in each of the following settings? So first we want a 95% confidence interval based on an SRS of size n equals 12. Well, you know that 95% means there's 5% remaining. So first we have to figure out what percent we would have in our tail, one of our tails. So there's 5% remaining, which means there's 2.5% left on each tail. So in table B, we look at the row corresponding to the degrees of freedom of 11, 12 minus 1, our sample size minus 1. And then since our upper tail probability is 0.025, we go in our table B, you should look at this, and t star is going to be 2.201. That's our critical value for t. If we want a 90% confidence interval from a random sample with 48 observations, when you go to the table, you'll see that 47 is not there. So we look at the row 40 and we look at 0.05 as our upper tail. So the corresponding critical value is 1.684. Okay, so here we go. For this one, we want a 90% confidence interval based on an SRS of size 10. So our degrees of freedom is going to be 10 minus 1, which is 9. Our upper tail, since we have 90%, we have 10% remaining. Divide that by 2, gives us 0.05. So going to table B in the back of your book, you'll see in the calculator how to do that here soon. But for right now, we're going to use the back of the book. This is actually on page 35 of your packet. It got out of order. So when I go to the back of the book, I get a T-star of 1.833. For letter B, our degrees of freedom would technically be 95 minus 1, which is 94. That doesn't show up in our textbook, so we have to move to, I think it's 90. Let me double check. We have to go to 80. So when we go to 80, we are going to, we have 1% that we have to divide by 2, so that's 0.01, so that's going to be 0.005 that we're looking at. And we're going to the row with 80, so I have 2.639. If you use your calculator, it's going to give you a slightly different answer. I used my calculator for part A, so if that's slightly off, that's why. Okay, so back to page 34, we now have conditions for estimating mu. As with proportions, you should check some important conditions before constructing a confidence interval for the population mean. So, conditions for constructing a confidence interval about the mean. First, it has to come from a random sample or a randomized experiment. The 10% rule still has to be accounted for. If we're sampling without replacement, check that the sample size is less than or equal to 1/10 of the total population. And again, if we're using mean, the population has a normal distribution, or the sample size has to be large, greater than or equal to 30. If the population distribution has an unknown shape and n is less than 30, use a graph of the sample data to assess the normality of the population. Do not use T procedures if the graph shows strong skewness or outliers. So for this, if n is greater than or equal to 30, you can use the T distribution, no problem. If we have outliers and strong skewness and our sample size is less than 30, then we cannot use a T distribution. This is on page 36. It says determine whether we can safely use a T-star critical value to calculate a confidence interval for the population mean in each of the following settings. We want to estimate the average time in minutes to order and receive a regular coffee at the local coffee shop. The time for randomly selected visits to a local coffee shop are shown in the dot plot below. Well, you can look at our dot plot and you can see there's only 5 data points. So n is less than or equal to 30. The sample size is really small. And 4 of our dots are clustered together, so it looks like that last dot out here looks like it's probably an outlier. So the answer is no. We cannot use T-star because the sample size is too small and there appears to be an outlier. In the second one, we want to estimate the average height of the high school students. The box plot below shows the distribution of heights in centimeters for for 100 randomly selected students. Well, n is greater than or equal to 30, so we're good to go. We can use a t-star. Doesn't matter that there's outliers here, because our n is greater than or equal to 30. And the last one, a middle school counselor wants to estimate how many minutes on average students spend doing homework. A histogram of the amount of time doing homework the previous evening for a random sample of 20 students is shown below. Well, our n is only 20, but if you look at this graph, it's not really skewed. It doesn't have any outliers. Everything looks like it's kind of compact together. There's no one thing that's way out there. So we're going to say yes. This graph has no skew and no outliers, so even though n is less than 30, we're still good to go. Okay, that's where we're going to stop for today. Jot down any questions, comments, or concerns, and bring them to class tomorrow.